cross-validation, binary choice model. Actually, before the cross-validation, we have to separate out. Usually, in data science, we separate out our data into the 3 different sectors. This is what we call is a training. And here, this is the validation. And finally, this is the test. You may already have some experience, but here, training is we use this data to build up our model. Any model, logistic regression, just linear regression, or random forest, whatever the machine learning model, we use this data to find out our parameters, right? And then why we have a test data separate out is since we use a training data, maybe your model is just pretty good at only on your training data. That's possible, right? So actually, this is the overfitting. Yeah, overfitting problem. So if you have overfitting, actually that is pretty good on your own data, but in general, that's pretty bad model. So that's why we have to separate out. We cannot tell it's a bad model in general, but only perform well in my training data. It's possible because you use that data to build a model. That's why we have to separate out data set using when we evaluate our model itself. But what is a validation model? The validation model is when you trying to find out certain method. You have to find out select what kind of predictor you're gonna use, or what kind of the parameter, hyperparameter. So that is not the B0 here, like B0, B1. This is the parameter we are looking for, right? X1 plus X2. So B0, B1, B2 is our parameter we're trying to estimate. But how many predictor we're gonna use? That is kind of thing is what we call is the hyperparameters. So we don't know which one is better. Then using this validation data, usually we just modify our model. Okay, but so we have used the accuracy rate to assess the performance of classification model. The performance measure will calculate it. Sample also used in the estimation. Model may perform very well in our sample, but perform poorly when make out of sample prediction. That's what I meant. So that's why we have the test data separate out. But here, this is the validation, cross-validation model means it's including all of this. But when we divide the 3 different things of validation, is not only for the performance measure. Again, I mean, when we try to find out what is a good hyper parameter, we have to evaluate. So that's why we have to have a separate data set here. This is a typical setup. When we have a data, we will use like a 30% of the data for the training, 20% for the validation, 10% for the test data, and so on. So you have to separate out. So here, this is evaluate. So you separate out the data set into the training and validation, and then training set is used to build the model, and then validation set is evaluate or validate the model. So that's the fair comparison. So most of the part will be used as a building a model, but a little bit of the part will be using the validation set. Here, the explanation of validation set is including the test data. This is more like a test data. So as you can see here, maybe you can use not all of the 500. You will use only first 375 for training, which one is as a building model. And then 125 for validation. Here, validation is the test or evaluation. And then if you find out the if there is some parameter, so we consider two different models. So respond, hyperlink, and character, all of them. And the model 2 will be dropped the predictor variable, which is not statistically significant. So since model, if you run the model, build a model, as you can see, this is like a 7%. This is a 7%, which is greater than 5%. So in the second model, we drop the character, right? And then you make a prediction, and then you calculate the accuracy rate using, again, this is the later 125, right? This is 376 to the 500. And then you compare to the accuracy, and now you can see model 1's accuracy is better, but model 2 is simpler, so actually you cannot tell. But if we have adjusted R, you can easily tell which one is better. But here we don't have such a method, as far as I know, like adjusted R. So you have to just decide the simpler model or more accurate model. So in R, how we do is use a training data and validation data from 1 to 355, and then comma. I don't type in anything here, which means it's all. So usually you have to specify 1 to 375, comma, and then you have to specify, this is a row. You have to specify which column. You have to, if you do this is a column I'm collecting only 1, 2, 3. However, if you wanna collect include all of them, then you don't have to write anything. Then it means it's all column. So first up to 375 rows go to the test data, and then the remaining 125 rows go to the validation data, and we will developing the logistic regression general linear model. SPAM is a recipient, hyperlink, and characteristic, and family binomial to make a logistic regression, and using only training data. And then when we do the prediction, we use validation data, and then you can find out what is the accuracy. This is the accuracy rate. So when we hold out, actually that will affected by which set we use the training data and validation data. So this is the it's a more complicated thing. So I will not use this one actually, but this is what we call the k-fold cross validation method. So you do it first. This is a training, and then this is training, this is validation. But you can use this is training and this is validation. You just keep changing the data selection, and performing the method is k times, and then you calculate the average. So if you do it more and more, it's more reliable, but actually this is kind of the tedious task. So you just need to know there is a k-fold cross validation method. Then using the same data, you just changing the training data and validation data. Okay, so what observation will go to the validation data is it keep changing, right? and then you can find out the accuracy is a lot different. It's like a 68 to the like 84, 65 to the 80, a lot different. So you can calculate the average, then you can tell, right? This is what we call the cross-validation, K-fold cross-validation method. So now accuracy, consider the imbalanced data. So this is the key point. When the data set, there is a 95% of the yes, 1, and only 5% is 0. And then I created a prediction model that predict everything is yes and 1. And what would be the accuracy rate for this prediction model? This is a lousy prediction model because I just predict everything yes. I don't need a model. I just say everything will be yes. Since in outside data, there is a 95% of response are yes. So what will be the accuracies? It will be 95% accuracy. Right? But even, no, this is a pretty good predictor, but that's not what we want. I don't want to just predict everything yes. That's useless, right? But if you take a look at the accuracy, this is 95% accuracy. So we need more than just accuracy rate. Accuracy rate is a pretty good information in general, but maybe we need more than just a simple accuracy rate. So we bring the sensitivity and specificity. Okay, sensitivity is accuracy is the most common metrics, but when this is a pretty balanced data, then accuracy will be pretty good measure. However, as I told you, if the data has a skewed, a lot of yeses, a lot of very small no, or opposite case, very small yes and a lot of no's, then accuracy doesn't tell you everything. So we created a sensitivity and the specificity, and also there is a different measure. It's a recall and precision. So so sensitivity is the proportion of target class cases that are classified correctly, and then proportion of non-target classes cases are that classified correctly. So if you just read these two sentences, this is confusing.